Assalamu alaikum wa rahmatullahi wa barakatuh. My name is Abdullah Uthman from E1S1. My friends and I are going to do a presentation about electrolytic water splitting. Bismillahir Rahmanir Rahim. Let's begin. Electrolytic water splitting represents a groundbreaking technology in the realm of clean energy. By applying a continuous electric current through a cell filled with water and a suitable electrolyte, water molecules dissociate into their fundamental components, hydrogen and oxygen. The hallmark of this process is its ability to produce green hydrogen, which emits nothing but water vapor when used as fuel, thereby dramatically reducing carbon emissions and supporting global climate goals. Additionally, excess electricity generated from renewable sources such as solar and wind can be stored as hydrogen, enhancing energy security and mitigating grid fluctuations. This technology also unlocks vast economic opportunities by fostering industries and jobs related to hydrogen production, storage, and transport, while driving research into more efficient, cost effective materials and devices. Secondly, we're going to talk about the scientific principles and basic laws about electrolysis. Water electrolysis rests on Faraday's two laws, which quantify the relationship between electric charge and the amount of substance produced at the electrodes. Faraday's first law states that the mass of a substance produced, M, is directly proportional to the total electric charge passed, Q, and the equivalent weight of the substance, E, divided by Faraday's constant, F, M equals Q times E divided by F. The second law, the Faraday's second law, relates the equivalent weights of different substances to the charge required to produce them. These laws are embodied in the overall reaction 2HO 2H2O equals 2H2 plus O2. Theoretically, this reaction requires 1.23 volts, but in practice, 1.8 to 2 volts is needed to overcome internal resistance and heat losses from side reactions. Parameters such as solution temperature, viscosity, and pH influence the required voltage and reaction rate. Higher temperature reduce water viscosity and lower the voltage needed. Yet excessively high temperature can accelerate electrode corrosion. My friend Ahmed is going to complete the presentation and thank you.
بسم الله الرحمن الرحيم السلام عليكم ورحمة الله وبركاته. My name is Ahmed Adil and today we have presentation about electrolytic water splitting. Me and my friend will talk about it. So as we saw earlier, my friend Abdullah talk about the introduction and scientific principles. So I will skip it. We'll continue in components and equipment. A typical electrolytic cell comprises one first thing is the cell vessel, which is constructed from corrosion-resistant material, an example, engineering polymers or acid-resistant coated steel to contain the electrolyte and gases, which is this one. This one here we call the cell vessel. And we have also electrodes, which are anode and cathode. The anode is a platinum or oxide-coated titanium selected for its oxidation resistance, and the cathode is a stainless steel or high-purity nickel chosen for its reduction tolerance. Here, as you can see, this is the cathode and this one is the anode. Electrolyte, sulfuric acid solution, sodium hydroxide solution, or a saline solution to enhance conductivity and minimize resistance. And next we have a cooling system, water or air cooling to maintain optimal operating temperature and prevent overheating of the electrodes. So that's the reason this one is not closed here. It's open to the air, so we can cool the cathode and anode to obtain the temperature that we need. And lastly, we have monitoring and control, which are real-time sensors track voltage, current, and also temperature, enabling dynamic process adjustment to ensure stable performance and high purity gas output. So we will move to electrode reaction and gas separation. Upon energizing the cell, oxidation and reduction occur simultaneously, sorry, at the anode. Oxidation. So here we can see this half reaction, 2H2O in the reactant, and in the product we have O2 gas plus 4H gas ion and also 4 electrons. And also 2H2, this is liquid, which is water. Oxygen gas involved leaving proton in the solution. As you can see here, this is the oxygen leaving. And on the other side, we have the cathode reduction. So here we have 4H2, four molecules of H2O liquid plus 4 electrons in the reactant, and this two must be here actually. So in product we have 2H2 gas plus 4OH minus gas. So hydrogen gas form alongside hydroxide ions. So this is the hydrogen gas leaving. To collect each gas without mixing a proton exchange membranes or a mechanical barrier permits ion flow but separates the gas streams, channeling hydrogen and oxygen into individual storage tanks or piping system. So this is what we call the exchange membranes to not to separate the hydrogen gas from the oxygen gas. And I will leave you with my friend, and that's it.
Assalamu alaikum warahmatullahi wabarakatuh. My name is Hamza Abdulbaki, Hamza Ahmed from the section E1S1, and I will be taking the next part in this presentation. Now, the factors affecting operational efficiency of this technology. First of all, let's say current density. Higher current boosts gas production until saturation, beyond which excessive heat and electrolyte crystallization occur. Secondly, the applied voltage must exceed the theoretical minimum but remain low enough to limit our potential losses in the process. Thirdly, the electrolyte composition and pH. It impacts ion transport speed and overall conductivity. The design, fourthly, the design of the electrode, porous or rough surfaces increase active area, reducing the localized current density. Fifth, the temperature. Elevated temperatures lower the water viscosity and voltage requirements, but risk accelerated electrode degradation. Sixth, pressure. Operating under elevated pressures can increase gas density and enhance production rates in industrial settings. Speaking of industrial settings, what are the applications of this in the industrial world? Let's take the ammonia synthesis, for example. In the Haber-Bosch process, green hydrogen reacts with nitrogen under high pressure and temperature in the presence of an iron catalyst to produce ammonia. This ammonia serves as the cornerstone fertilizer in agricultural operations and prospectively as the hydrogen carrier that facilitates transport and storage of green hydrogen.
Bilal Hussam Baggar, Bismillah ar-Rahman ar-Rahim. Despite its promise, water electrolysis faces several challenges. First, electricity cost represents the largest component of green hydrogen's overall cost. Material durability Electrolytes, catalysts, and membranes must withstand thousands of operating hours without significant degradation. Thirdly, cell efficiency, reducing thermal and electrical losses, demands improved cell design and advanced cooling techniques. Fourth, infrastructure, developing a safe, efficient, and cost competitive hydrogen distribution and storage network. In conclusion, water electrolysis stands at forefront of sustainable hydrogen economy, producing clean fuel and enabling flexible storage of renewable energy by combining environmental benefits with economic and technical advantages, and with ongoing advances in catalysis development, cell design, and materials. This technology is poised to achieve greater cost, efficiency, and wider adoption, assuring is a cleaner global energy future. Thank you.